Thank you, everyone, for joining this online conference today. Dear Dr. Meng, dear Dr. Katayama, dear participants and colleagues. On behalf of the German Research Foundation and our co-organizers, the German Center for Research and Innovation Tokyo and Hiroshima University, I would like to extend a warm welcome to our third Heinz Maier-Leibnitz-Prize online conference. Today, we will hear keynotes on approaches in Germany and Japan in the field of quantum physics and quantum technologies. My name is Raoul Wagner, and I am Program Officer at the International Affairs Division of the DFG. Please allow me to say a few words on the occasion of this event, which we hold in honor of our prize winner of 2022, Dr. Tobias Meng at TU Dresden. The DFG has been awarding researchers in the starting phase of their careers with the Heinz Maier-Leibnitz-Prize since 1977. The prize is awarded for pursuing curiosity-driven research and recognizes outstanding achievements. It is intended to assist prize winners in excelling in their scientific careers. Supporting outstanding researchers on early career stages is one of the pillars of our work at the DFG, also within our international cooperation. Therefore, we are more than happy to have Dr. Haruna Katayama at Hiroshima University as our second speaker today. She too is a well-recognized researcher in her field and one of the few women conducting award-winning research in physics in Japan. Quantum as a topic is very much in the focus of international funding activities as well. In this year's spring, we launched a call with the Japan Science and Technology Agency for joint projects in the area of quantum technologies. Starting from 2025, we will fund 2 large-scale projects with German and Japanese PIs over a period of 5 years. Now, I hope you will all enjoy the talks today and engage in lively discussions. From here on, I will hand over to the MC of our event, Deputy Director at DFG Office Japan, Myra Bauersachs.
Yeah, thank you, Raoul, for the kind introduction to our event today. First, I would like to briefly talk about the program today. We will hear 2 keynotes from Germany and Japan and have a few questions after each keynote. In the second part, all participants are invited to join the discussions with Tobias Meng. You can post questions in the Q&A or on the German screen, the F&A section during the talk. My colleague Eiko will pick up the questions later during the discussions. You can also directly ask questions by clicking on the raise your hand button, Handheben button. We will unmute and call you then. When you are speaking, we will only hear your voice. Your screen won't be shown. So much on the housekeeping rules for today. And now let's dive into the first presentation by Heinz Maier-Leibnitz-Prize winner, Dr. Tobias Meng from TU Dresden. Tobias was awarded the prize in 2022 for his groundbreaking research in the field of topological phenomena in quantum materials. He's also leading an Eminöta junior research group on quantum design within the cluster of excellence CTQMAT, Complexity and Topology in Quantum Matter, which is a cooperation of Julius-Maximilians Universität Würzburg and Technische Universität Dresden, and is funded by the DFG. To understand the complex behavior of quantum materials, Tobias takes an exceptionally broad approach. In his talk today, he will share his insights about the quantum frontier with us. Tobias, with this, I would like to ask you to start your presentation.
Okay, wonderful. Thank you very much for this kind introduction. It's a great pleasure to take part in this wonderful event. I'm very happy to see so many interested people. So let me begin by introducing myself shortly. I'm Tobias Meng, and I'm heading the quantum design group at the Technische Universität Dresden in Germany. And in the next couple of minutes, I would like to give you a hopefully accessible introduction to my field of research and to some of the things that my team and I did in the last couple of years. Now, to put everything into a broader perspective, let me begin by pointing out an obvious fact, which is that a lot of technological progress builds on scientific breakthroughs. And one example is shown here on this slide. You see a computer prototype, ENIAC, that was completed in 1945. And as you can see, at the time, this computer filled an entire room, and its computational power was quite limited if you compare it to what our computers can do today. And this progress has been largely powered by a lot of thorough scientific work and also some revolutionary breakthroughs, such as the invention of the transistor. And so looking forward, one exciting question is to ask, what is going to be the next big technological revolution? And I have a dream that I share together with colleagues from around the world, in Japan, in Germany as well, which is to actually bring quantum physics much more onto the center of the stage and use it much more in technological applications. To understand what we mean by that, let me give you just a brief introduction to quantum physics. So quantum physics explores the world on the smallest scales. It's the scales of atoms and molecules, for example. And on these scales, there are certain phenomena happening that have no analog in our everyday life. And the dream is now to use these phenomena, these new phenomena, to do something good with them. In this talk, I do not have the time to introduce quantum physics in great detail, but I have a recommendation for you if you're interested in the topic more generally. So together with our colleagues from Würzburg, we developed a smartphone game app that you can download on your favorite app store. It's a game app that, well, tries to teach you about the wonderful world of quantum physics via little puzzles. It's originally been designed for kids, but I think it's great fun to play. And so along the way, you pick up some of the interesting quantum phenomena that we work with every day. Now, to get back to the theme of this conference, quantum technology, let me begin by defining what that is. Namely, for me, quantum technology is any piece of technology that uses quantum physics to achieve whatever it does. One prominent example is the quantum computer. Here on this slide, you see a picture of a quantum computer prototype. This is, I think, quite a special piece of technology. And to tell you why that is so special, I would like to compare how this new type of computer works as compared to the ones that we have today. And so let's take a computer that we all know very well, namely our smartphones. Our smartphones are really just small computers. And if you ask your smartphone a question, for example, about the weather, then what your smartphone is going to do is it will translate that into its own native language. And that's the language of ones and zeros, a language of bytes. So let me represent, for simplicity, just these ones by red balls and the blues by zero balls. Meaning what happens if you ask your smartphone about the weather is that it translates this question into sort of a Morse code consisting of these red and blue balls. This is how our computers work today. We have bits of information, and every bit can take either one value, it can be red or blue in these pictures. What we propose is to make computers faster, not by having more of these bits or handling them faster, but to completely change the basic architecture. Namely, what we propose is to use so-called quantum bits. And these quantum bits, they are quantum systems. There are different variants of that, but what they all have in common is a beautiful phenomenon that is called quantum superposition. And that's something that is well known in quantum physics, and it means that quantum systems, including these quantum bits, they can have not just one value at a given time, but they can have multiple values at the same time. You already see from the simple picture that these quantum bits have a large set of possible values and therefore are potentially much more powerful than the simple classical bits that we have nowadays. And if you build a computer out of these quantum bits, then you get a quantum computer, and they are possibly indeed much, much more powerful than the computers we have today, because they use this power of quantum physics. For example, it's been shown that these quantum computers are, at least in certain cases, already much faster than today's computers. That goes by the name of quantum supremacy. But there are other huge prospects, such as quantum cryptography, a new way of secure communication that would be much, much more secure than the communication we have today, or even that quantum computers could really revolutionize the way we think about developing new medication and possibly contribute to curing diseases. So there are lots of prospects, but there are also big challenges ahead. And maybe one of the biggest challenges is something that we call decoherence. If we look at this quantum bit, what it means in practice is that these quantum bits, they forget very quickly. The information that you store in this nice color pattern gets lost very, very quickly. And that's, of course, bad. If you have a computer that loses the information that you store in it, you can't really use it very well. So one big problem is to make these quantum systems less forgetting. And so the reason why they forget is that they are pretty sensitive to what happens around them, to their environments. So at the end of the day, what we want to achieve, or one of the goals that we are pursuing, is to have our quantum systems being less sensitive to what happens in their environments. And this is where a recent revolution enters the stage. That's a revolution in physics, and that revolution was the advent of topology. Now, topology is really a discipline in mathematics. It's a mathematical theory. And putting it in very loose terms, topology is the theory for super robust phenomena. For a long time, topology hasn't really been connected to physics. But in the last, say, 20 years or so, it's been understood that topology actually does play a role in physics, and it plays a crucial role in physics. And this has also led to a number of Nobel Prizes. Now, if we look at what I've told you so far, then you immediately see a connection appearing. We have these phenomena that are beautiful, but extremely sensitive. And then we have this theory of super robust phenomena. So why not marry the two and try to create something that is beautiful, but also robust? And that is the research mission of my team. The quantum design idea is to take systems that feature topological phenomena that are interacting and are coupled to their environments, and then to create interesting quantum phenomena in them, to understand the phenomena, but also materials in which we can create them, and then also to control these phenomena such that they can be used. Our long-term vision is thus to explore fundamental material properties with the goal of enabling future functionalities, for example, in quantum technology. One example directly connects to the problem that I told you. So what I'm now going to do is I'm going to tell you about two little projects that we did quite recently, so that you get an impression of what it is that we do on our everyday basis. And the first one is about the coupling to the environment. So I told you that if you couple a quantum system to the environment, it degrades very quickly. The quantum computer forgets its information, for example, very quickly. And so you might wonder whether you can use topology to help against that. And that's actually something that you can do. We studied that in a number of cases, but one recent example is shown here on the left. This is a theoretical model. It's a model of a topological system called a Chern insulator. Essentially, it's a system, it's a two-dimensional systems in which you can put quantum particles and they can hop around. And the special thing is that this quantum system is lossy, so the particles that you put in there, called electrons, they can drop out. For simplicity, let me just represent that with a chessboard. So the quantum system is a little bit like a chessboard, and then we can put particles in it, here represented with this red dot, and the particles can move around in this quantum system, so they can hop back and forth. That's the basic setting. And then we looked at the situation that we initially completely fill this quantum system. So every possible spot is taken. Now, because we are in a lossy system, what's going to happen is that every once in a while, one of these particles will get lost. So one particle is lost, another particle is lost, maybe a third particle is being lost. And you already see where that journey is going. If you wait long enough, your system will be empty, all particles will be gone. And that's what we want to fight against. So what we then studied is how using the topology in these journey simulators can help you against that. And I'm just going to jump directly to the conclusions. On this slide, what you have is a comparison of the two situations, one where we do not have the topology helping us, and one where we turn on the topology that helps us. And initially, it might not look very different. Initially, you lose particles in both cases. But if you wait long enough, then something quite magical happens, namely that in the system without topology, everyone's gone, all particles are gone, everything has dropped out. But in the system with topology, particles remain. They happen to remain close to one edge, and so you might wonder if we have achieved here a lot, because there's only one strip of particles remaining. But of course, that depends on what you want to do with the system. If you're interested in having just a row of particles, this is perfect. This row is well, we call it topologically protected. So the fact that this system is coupled to an environment doesn't affect the particles on this edge at all. And so this showcases one example where topology helps you to really beat the disturbance that happens from around the system. We call that edge selective extremal damping, and that was one of our recent projects. So that's about an example about where we can create an interesting quantum system that is protected against the effect of the environment. Another example that I want to show you is an example of control, because it turns out that topological materials also offer you the opportunity to control their properties quite neatly. And so that is something that connects to a completely different physical setting, and it's something that connects to materials that exist. So the first project I told you was quite theoretical. This is more practical. There are certain classes of materials called topological semimetals, but you can just think of them as essentially some metal. Here you see on the left, you see the crystal structure and the sample, a photograph of a sample made of this material. But what we then thought about is the following situation. You take this material, just a cube of that material, and you connect it to a battery. And then what's going to happen is that an electric current will flow through that material. And we were asking, where exactly does the current flow? And can we influence where that current flows? And so that's what we did, what we studied in another project. Here you see 6 images. Each image is like a top view of the system that we simulated microscopically. You see a bright beam. That bright beam is exactly where the current flows. And then you see a white spot. And that white spot shows a region in which we apply a special type of strain. To simplify matters a little bit, just think of it as sort of pressing on that region with your thumb, with your hand. And so what we found is that if in these topological semimetals, you press on that material very far from where the current flows, the current goes through exactly, well, essentially undisturbed. But if you press very close to where the current flows, then you can make the current curve. And it turns out that it doesn't curve in some arbitrary way, but it curves in a very precise way that you can control very neatly. And as a fun fact, and that connects to the second presentation, the way the current bends is exactly identical to the way that light is being bent in the vicinity of a black hole. So there are some beautiful connections to other fields of physics, and Professor Kawabata is going to tell you so much more about the beauty of gravitational analogs in lab systems. However, I want to emphasize that this is not why we looked at this. We stumbled upon that sort of by accident. We were really interested in this aspect of being able to control phenomena in these topological materials. So those were 2 small spotlights, creating certain quantum effects in topological materials and controlling their properties. And we believe that by exploring the wonderful world of topology in quantum materials, we can lay the foundation for enabling future quantum technologies. I put a list of things that are maybe coming up in the next, well, hopefully years. Ultra-fast quantum computers is something that we discussed quickly. Quantum cryptography, Optimization problems are all around the world, and so quantum versions of that might be very helpful to look at. Ultra-sensitive sensors, new medication by quantum simulation, all of that are possible applications for quantum technology. And since quantum technology is still an emerging field, I'm sure that there are many, many more things that we simply haven't thought about yet. So I believe that's a very exciting field to work in. That concludes my presentation. Thank you very much for your attention.
Thank you, Tobias, for this fascinating insight into your research at Technische Universität Dresden. Research questions that you discussing with your colleagues at the Minuta group, and you were mentioning a few of the possible applications that can come up in the future. And amongst them were computing and also sensors for in the field of medicine. So could you again maybe explain a little bit more what the opportunities for the applications are there? So what can you do, for example, in the field of quantum computer or the field of sensors in the field of medicine?
Yes, thank you for that question. Very interesting. So I talked a little bit about quantum computers, and I should say that I'm not building a quantum computer. I'm researching sort of the fundamentals of materials that might help doing that. I would say my perspective on the field is that there is a lot of very exciting things happening. And there are first prototypes of quantum computers that can do wonderful things. But they are still in their very early days. So if you look back at the initial slide of my talk where I had this computer prototype, I think we're more or less at the equivalent of that stage. That doesn't mean that this is not a big achievement, and it's extremely impressive what the people who build quantum computers, what they have achieved already. So that means, however, that these prototypes, they are mostly at a stage where you make proof of principles. And there are some very interesting proofs of principles that have been done. I quickly mentioned the proof of principle for this concept of quantum supremacy or quantum advantage, which means that there have been specific problems that were given to a quantum computer, and then the quantum computer solved these problems presumably much faster than the supercomputers that we have around now. So that showcases some of the power that is in these machines. And another idea would be quantum simulation. So quantum computers, they have quantum physics built in already, which means that they are particularly good at simulating other quantum systems. And our regular computers nowadays, they're very bad at simulating quantum systems. Well, very bad, but it's hard for them. And so the hope would be to simulate quantum systems. Now, I said quantum systems are small systems such as molecules. And if you think about where a molecule is important, for example, then we get back to medication, because the active ingredients in medication are some molecules that, you know, connect to some receptors in your body or something. So learning about these quantum systems might also be interesting from that perspective. Another thing that is gaining some momentum is quantum optimization. So there, I would say the idea is that the world is full of optimization problems. If you think, for example, about a supermarket, you have a supermarket chain that has lots of stores, and then you have a truck that is delivering to the stores, then what's the optimal route to connect all of these stores, right? If we first going to go here or first going to go there, and then what's the second store to visit in order to reduce maybe the total time that it takes? That's a typical optimization problem. And you can phrase these optimization problems in a language that allows them to put them on a quantum computer. And so there as well, it's been shown that quantum computers can in principle do that. I believe they're not yet at the stage where they would beat the existing classical computers, but I am confident, and this is more of a say, a problem where people need to work on details and get things better step by step. And eventually, the hope is that quantum computers will overtake the classical computers. So that's about some of the things that quantum computers can do. About the sensing, there are also some beautiful quantum systems that allow you to do extremely sensitive, to create extremely sensitive sensors. And one example is sensors for magnetic fields. And magnetic fields is something that, for instance, connects to the neurons in your brain. It connects to your heart activity. And so that means that having these ultra-sensitive sensors might revolutionize some of the diagnostics in medicine. It might also be important for brain-computer interfaces, where you need to somehow pick up the electromagnetic activity, and these sensors might be a way to do that. So there are, again, lots of huge prospects, and the idea is that you just have a sensor that is very small but very, very sensitive. And yeah, so that's also a very, very exciting idea, I think.
Yeah, that's fascinating. It seems that it's really like these small scale areas where you can apply the quantum technologies that you lay the base for, as I understood it. So actually, we have come to the time of the next keynote, and I would ask everyone who has raised their hand and wants to ask a question to please keep that question in mind and carry it to the discussions that we will have afterwards. We are very much looking forward to discussing more about this fascinating talk by Tobias Meng. So thank you very much for the first keynote. I think that is a fantastic base for the discussions later on. And now I would like to come to the second talk. Our speaker from Japan, Haruna Katayama, is at the Graduate School of Advanced Science and Engineering at Hiroshima University. And Haruna's work is expected to contribute as well to the realization of next generation information processing and communications when applied to quantum information science. And Haruna too was recognized as an outstanding researcher. She was selected, for example, for the annual Asian Scientist 100 list in 2023 by Asian Scientist magazine. And she received the 2022 Japan Fellowship Award by L'Oréal UNESCO for Women in Science. And Haruna, we are also very much looking forward to your talk. Would you please start your presentation?
Thank you very much for the kind introduction. I am Haruna Katayama, an assistant professor at Hiroshima University. It is truly an honor to be here today. I would like to express my gratitude for this opportunity to share our research with all of you. Our work focusing on Hawking radiation, a quantum phenomenon that occurs in black holes. We have explored Hawking radiation from electric circuit as a key to bridging quantum physics and general relativity. Before starting my presentation, I would like to briefly introduce where I am from. Hiroshima is located in Western Japan, is known for its rich cultural heritage and beautiful scenery. One famous site is Itsukushima Shrine on Miyajima Island, a World Heritage Site built on the sea. You can see friendly deer walking freely there. Another World Heritage Site is the Atomic Bomb Dome, which was preserved as a reminder of the 1945 atomic bomb. Our university is located in Higashi Hiroshima City. Higashi Hiroshima is famous for sake. Since our campus moved there in 1993, the city has grown rapidly, and many students now live nearby. Hiroshima University is celebrating its 75th anniversary this year, marking 150 years since its predecessor was founded. I enrolled at Hiroshima University, completed my master's and doctoral program, and became an assistant professor in 2022. My research focuses on using electronic circuit to simulate cosmic phenomena. First, let me explain the background of our research. The unification of the four fundamental forces in nature is the ultimate goal of modern physics. So far, gravity remains the only force that has not been unified with the others. The primary barrier to unifying them is inherently incompatibility between quantum theory and general relativity. The two theories are difficult to be unified because they deal with different scales. However, Hawking radiation that occurs in black holes is attracting much attention as a potential bridge between the two fields. Here, I will explain what a black hole is. A black hole observes everything, and even light cannot escape from it. But what does it mean when we say light cannot escape? For example, if you throw a ball up from the earth, gravity will pull it back down. However, if you throw it with enough speed to overcome gravity, it will not return and will continue to fly away. In contrast, in a black hole, gravity works very strongly because it has incredibly high density. As a result, even fastest speed in the universe cannot escape. In general relativity, black holes can be thought of distortion of space-time. Imagine a flat surface with a rubber sheet. Pressing a marble on it causes the sheet to sag, corresponding to how space-time is distorted. A black hole is like a marble of extremely high density, causing a significant distortion and creating a hole. The boundary around this hole is called the event horizon. As I explained, nothing can escape from a black hole. However, Hawking challenged this idea by predicting that light can be emitted from a black hole. This seemed to contradict the earlier understanding. But Hawking's prediction is based on quantum mechanics, not classical physics. In quantum mechanics, particles and antiparticles are constantly created and annihilated in pairs in a vacuum. Near the event horizon, one particle can escape as a Hawking radiation, while the other falls into the black hole. Hawking radiation is a phenomenon that combines general relativity and quantum mechanics. And its observation could help unify the two. However, it is difficult to detect because the Hawking temperature of black hole is extremely low. Therefore, we have developed a theoretical framework for detecting Hawking radiation in an electric circuit. This will contribute to the unification of quantum theory and general relativity. Here is the basic idea of an analog black hole. Let us consider the fish swimming upstream in a waterfall. In still water, the fish swims at a constant speed c. Meanwhile, the water flow changes with position. The black composite vector shows the fish's velocity in flowing water. The position with zero velocity is the event horizon. Upstream of the horizon, the fish can swim freely, while downstream, it is carried away, similar to a black hole. The key to mimicking a black hole is to vary the velocity depending on the position. To achieve this, we use electromagnetic waves that propagate within the electric circuit. The fundamental structure of the electric circuit is an LC circuit, which combines an inductor L and a capacitor C. Initially, we assume the capacitor is charged, creating an electric field like this. Electrons move along this field, and as they reach the plates, the field weakens. Eventually, the electrons move to the opposite side, and the field disappears. During this process, the inductor has a property that resists changes in current, so it attempts to keep the current flowing. This causes the polarity of the charge to reverse, and the opposite phenomenon occurs continuously. The change in the electric field generated by the capacitor induces a change in the magnetic field. In this way, electromagnetic waves are generated. A circuit formed by connecting the basic circuit is called the transmission line. In this case, the electromagnetic wave propagating along the transmission line like this. Its velocity is determined by the parameter of the inductor L and the capacitor C. The electromagnetic waves can be linked to the flow of water. We consider the electric circuit where the inductor is replaced with a Josephson junction made of superconductor. In this case, the parameter L varies depending on the position. As a result, the velocity of the electromagnetic waves corresponding to the water flow of the water, changing depending on the position, allowing us to create a flow similar to that of water flow. In this way, we have created analog black holes. In this system, two horizons are formed. Since one cannot move up from downstream, it behaves like a black hole, while one cannot enter the waterfall from downstream, resulting in a white hole, which possesses the opposite properties of a black hole. Additionally, to further amplify the Hawking radiation, we constructed the black hole laser. In this setup, we introduced the metamaterials. This allows for the creation of fish that swim against the flow of waterfall, enabling them to move between the two horizons. The horizon functioned as a resonator, thereby amplified Hawking radiation. This black hole laser is expected to serve as a new light source in quantum information technology. This is the end of my presentation. Thank you very much for your attention.
Haruna, can you unshare your presentation? Yeah, I think it was just a little time lag. Thank you so much for this fascinating explanation of your research. For a layperson, it's really difficult, but actually, when I saw your explanations about the fish and the waterfalls, there were some phenomena described in science fiction that I now finally understood what they were referring to. So if you're watching, for example, the three-body problem on Netflix or so, I think you will recognize some of the problems described here. Outing myself as a science fiction fan. And now I think it's also amazing how you build experiments on such a small scale to understand big physics problems. And we have a few questions for you as well that go a little bit deeper into your research. So the first question would be, in your field of research, which is very cutting edge and hype right now, where do you see the biggest challenges, especially for researchers on early career stages?
Yeah, thank you very much for your question. My research field is at the intersection of condensed matter physics, cosmology, and relativity. Mastering and applying knowledge from these areas is a big challenge for early career researchers. I still have a lot to learn myself, and every day is an opportunity to gain new knowledge. However, this interdisciplinary field holds an potential to generate a new perspective and phenomena that have never been discovered before, and I find that possibility very exciting. I believe it's important to stay open-minded and flexible in thinking without being constrained by existing knowledge.
Yeah, thank you. I would agree, of course, for as a representative of a funding organization that is promoting and fostering a curiosity-driven research. So not being constrained by existing knowledge and being curious about new findings is, of course, important in your in research. And I'm also glad that you are mentioning is an interdisciplinarity, because this is also one of our focuses when we are doing events between Germany and Japan, to add and offer new perspectives. And I have another question for you that I will read out now. Where do you see potential for future research in your field, and where do you see the potential of international cooperation there specifically?
Yeah, I see potential not only in mimicking a black hole, but also in simulating other cosmic phenomena using electronic circuits. For example, I am particularly interested in a phenomenon of the expanding universe during the inflationary period, shortly after the universe's birth. Recently, I discovered that we can simulate the universe expansion using electronic circuits. While we cannot directly observe the beginning of the universe 13.8 billion years ago, by simulating this situation with our circuit, we may be able to unlock the mystery of the early universe. International cooperation is essential for this research, as it requires the expertise from multiple fields.
Fantastic. So we, of course, encourage international cooperation. So if anyone is interested, like, get into contact with the speakers as well. And just very briefly, because it's interesting to see how your research relates to the bigger picture, can you point out how you draw conclusions from your micro scale or small scale experiments to the bigger phenomena like black holes in the universe?
Yeah, we can consider an analogy between our analog black hole and a real black hole because the underlying equation governing both systems are the same.
Yeah, thank you very much, Haruna. That was also a very, very interesting talk. Thank you for contributing to our event today. And we would like to move on now to the discussion again with Tobias. And
Thank you very much.
there were two. Thank you very much. That was fantastic. If we were in a room, we would give you all a round of applause. We do it virtually. And we're moving on to the discussion now with Tobias. And we had two questions before during the talk. So I would ask my colleagues if Andreas Deschner is still online to ask the question to Tobias Meng, I would ask my colleague to unmute you and you can then speak and we will hear your voice. We will not see your screen.
Hi.
Maybe we try that.
Can you hear me? Andreas Deschner here, also from the German Research Foundation, incidentally. Yeah, it was actually by accident that I raised my hand, but nevertheless, I do have a question. So I was wondering how, say, in the future, your research could connect to quantum technologies or the applications. So is this in making qubits, or where do you see the connection?
So let me put it this way. So the quantum technology is, I would say, still an emerging field. There's lots of beautiful things that have been done. There are lots of fantastic ideas, but lots of open questions still. And some of the open questions are quite fundamental. So what my research is trying to do is not so much to sort of take a concrete quantum technology system and optimize it, which is a hard enough task. But I'm more interested in the foundations of that. And so one point that I mentioned briefly is, for example, how do quantum systems, how do they connect to their environments, to their surroundings? How do the surroundings disturb them? And how can we understand fundamentally the ways in which we can protect these quantum systems from these disturbances? And so that is one of the points that maybe connects to future technologies, but that I think is fundamentally very important to address right now. So I try to contribute to laying some of the foundations that are then later used. I always like to have applications in mind as a long-term perspective. But I think there are other people who are much better at taking these theoretical considerations from us and then building something actually. Yes, so it's a collaboration there as well, if you want.
That sounds interesting. So you would say then that the research, the basis that you are laying there, it needs then a technology transfer, so to say, to bring it into the application. That would be a next step. Good.
Yes, absolutely.
Yeah. Fantastic. I would like to pick up another question from the audience before we read out a few more from the Q&A. I see Niklas Kostelidis raising the hand. Colleagues, can you unmute him? Okay, you should be able to speak now.
Can you hear me?
Yes, fantastic.
Thank you for the talk, first of all. I'm from the Technical University of Munich and I'm doing my master's in Japan. And yeah, I don't really have that much connection to quantum technologies. That's why I have like a really basic question, I think. So as I know, like quantum computers are required to be heavily cooled, for example, like to a few millikelvin. So I guess this is used for not disturbing the system, right? I mean, you had the example of the melting ice cream cone. And I would assume that the research you do is also has the same purpose, but to not have to cool the systems to such a degree. Because when we think of like technologies like smartphones, for example, it would be not feasible to like cool them with nitrogen or whatever. So do you actually want to implement your technologies in future devices like quantum smartphones maybe? And do you actually see that happening in the future? Because there's this IBM prediction from a few decades ago, I think, where they said, oh, we will only need 5 computers in the future. But now everyone has a computer now. So first of all, do you think your technology will be used in actual applications like quantum smartphones? And do you think that something like a quantum smartphone will even happen?
Okay, so these let's say basic questions, they're never really basic. They're always the most complicated ones. Lots of things I think that you mention and that are all very important. Yes, indeed. So the prototypes for quantum computers that exist nowadays, they are machines that are sort of heavily protected, and so protection by cooling is one technique, and so ideally you would like to have a system that doesn't need all of these layers of protection around it, that doesn't need to be cooled to minus 270 degrees Celsius, and that's a big thing to ask, but it's one of the questions that connect to the research of my colleagues and I. And so, well, making a prediction about the future is always complicated. I'm optimistic that lots of exciting things will happen. I do not want to say that you will have a quantum smartphone in 20 years. I think the next step is more towards, if we talk about quantum computers, then it's more towards building better quantum computers that might still require a very complicated laboratory to run them. But then to place them sort of in the vicinity of another supercomputer and to integrate them with the supercomputer, and then there will be certain tasks that the supercomputer will outsource to the quantum computer, and you can access the quantum computer sort of as a service. You submit your quantum problem online, and then it's going to be treated by that combined cluster supercomputer and quantum computer. That might be one way of moving forward. Now, bringing that sort of really to the everyday life, well, I'm not sure about whether that's going to happen. It doesn't mean that it won't, but there's a lot of challenges to be overcome here.
Thank you, Tobias, for the answer, and Niklas for the interesting question. I think it's good to hear that you have things to look forward to and you are striving to achieve. Of course, it takes often a lot of time to bring something from the basic research into the applications, but we are seeing a lot of progress, I assume, and I think as a layperson. Next, I'm seeing Axel Karpenstein raising his hand. Axel, you can post the next question, and then we pick up one question from the Q&A. We did not overlook that. So Axel is next, and then the Q&A question.
All right. Thank you very much, Myra, and thank you very much to the two speakers. I'm a layperson, but I'm a very curious and interested layperson, so I profoundly enjoyed both presentations. And I have a question to each one of you. Maybe first, Dr. Meng, since you went first, Tobias. Since you had this modification, quantum computers can be very, very fast in some cases. And I suppose there still is a lot of room and a lot of applications for traditional conventional computers. And I believe that there are also hybrid systems, right, where quantum computers and conventional computers work in tandem. So I'm wondering, for me as a layperson, what are the areas where each can show their strength? And where do you see the potential for hybrid systems? And what direction in general would you predict? Will both be sort of fundamental technologies for science, or maybe also for daily life applications? There's one question, and the question to Dr. Katayama, to Haruna. I believe you're sort of diving into the general theory of everything, if I'm not mistaken. But you're connecting quantum phenomena with electric magnetic waves. You're fusioning quantum physics with general relativity, I think, if I understood you correctly. I think theoretically this is already a very exciting field, but I'm also very curious about practical applications, and especially if you're modeling black holes and the phenomena related to it. What would you say are the implications, for example, for space travel or for our ability to explore space in greater depth? Thank you.
So since you addressed me, let me start. So I said some cases, yes. So what I to recall, so what I said is, quantum computers have been shown to be faster in some cases, and that's a statement that needs a debate on its own. Whether that's actually true, to which degree it's true, how much faster they were, there's a debate about that. What happened was that these quantum computer prototypes were built, and then essentially what people did is they thought of a problem that is particularly good for the quantum computer and maybe particularly hard for the non-quantum computer, and then they showed that the quantum computer can indeed solve that quite fast. And later there was a debate about, if we put as much time and energy in optimizing the existing computer to solve that problem, wouldn't it maybe be similarly fast? So the degree to which quantum supremacy, so the fact that these quantum computers are faster than our actual computers, the degree to which that has been shown in practice, that's a question that is, I think, still of fundamental research interest, and to push that. I don't believe. It is certainly true that you can actually show mathematically that if you do things right, then for specific tasks, quantum computers are much, much faster. And there is a list. It's not a very, it's not an infinite list, but it's a list with more than 3 entries of problems for which it's been shown that quantum computers are much faster than classical computers once they are up and running as they should. So you can ask, for example, let's take the example with the stores. If I have just 2 stores, then I can quickly find out where I should go first and where I should go second. If I have 3 stores, then it also works. With 5 stores, it also works. But if I have 10,000 stores, then it will take a long time to check all the possibilities. And so the idea is always to look at the problem, but make it bigger, and to ask, how much more time do I need for solving the bigger problem as compared to a smaller problem? And that is where then quantum computers will become. So there are these problems where it's been shown that for some of these problems, that if you make it bigger, the quantum computer just takes comparably less and less time than the classical computer. And so eventually they just have to beat them. And so for these problems, that's where they one of the areas where they can excel. Of course, there are other areas where it's maybe not necessary, or where it's still cheaper and more easy to build a big supercomputer. Connecting back to the question of quantum smartphones, I don't know if they will exist, but you have to ask, what's the actual benefit? So if I just want to stream Netflix and send emails and maybe every once in a while, because it's a phone, have a call, then maybe what I already have is enough. It also connects to more fundamental questions, like what's, for example, the resource consumption that such a machine would have. If I need to put a lot of resources into cooling it, into running it, then is it maybe not better to use the existing computers, because there's, the world is full of complementary problems that not always have the same solution. So if we look at the energy consumption of the internet, that's huge. And if we want to enlarge that by exponential factors with quantum computers, that's not a good idea either. So at the end of the day, it's going to be, we'll see. There are certain aspects where quantum computers are good. and there we will use them. And others where maybe we don't need them, or where the classical computers are maybe comparably good. And then we'll use the most efficient solution, the best combination of all worlds.
Thank you very much for the question and the answer. I'm also grateful that you kind of draw also a connection to the sustainability of all the systems, that you make use of the most sustainable solutions and combine them to have the best effect, I guess. Haruna, there was a very imaginative, I think, and a long question by Axel. A little bit of time passed already, so I will rephrase it and maybe you want to answer them. So Axel was asking about the possibilities of drawing conclusions on practical applications from your research on the small scale black holes to imagine maybe new ways of space travel. Do you see a connection there? What would you say to this idea?
Thank you very much for your question. In our analog black hole, we just simulate the metric of space-time. It's a curved space-time, like a black hole. So I don't think we can consider the space travel in our analog black hole, actually.
Thank you very much for the answer. Still, I think it's great to make mind experiments and imagine ways. I guess it's also something what researchers like to do.
Yes.
Yeah, thank you very much for the answer. We have one question in the Q&A that I would like to ask my colleague Aiko to read for us.
Then we have a question in English, so I'm going to read it out in English.
You propose to use topology to fight against the gradation of information to the environment, but you have not mentioned temperature effects. For an application, we might need to operate it at room temperature. So how sensitive is topology to temperature? It was raised during the presentation of Tobias.
Yeah, well, very interesting question. So I would say that topology and temperature, it's not like an immediate connection, but as a general rule of thumb, the hotter the temperature, the harder it is to observe any kind of quantum phenomenon, including these topological quantum phenomena. And indeed, there is the hope to make these quantum phenomena more robust using topology. But temperature is an obvious concern, as we see when we look at the prototypes. It's something that, so topology in general helps you to make systems more stable. But temperature is always bad, if you want, for a quantum physicist. It's definitely an issue, but as I said, maybe the real applications are not going to be at room temperature. Let me give you one example, a very practical example. If you, so I injured my arm some time ago, and so I went into an MRI scanner to get that scanned. And MRI scanners often use a quantum phenomenon called superconductivity, which also happens only at very low temperatures. This doesn't mean that these machines doesn't exist. It just means you don't have one at home. You have one at the hospital. And then these people there, they can operate it. And they take care of making it work. And similarly, other quantum phenomena might require that.
Yeah, thank you very much for the answer to this interesting question. Speaking also on the scale of the machines or the environments that we need to make use of these quantum effects. And we have another question in the chat referring to, I think, to this cybersecurity topic. Eiko, will you read that out? And I think we have even another one. So there are 3 now. So maybe the first one, and then we will introduce the next.
Okay, the second question is the practical case is not many here, I thought. It's useful information security. Do you know any cases?
So we need to define what practical means, I guess. I think that a lot of this technology is still really at the prototype stage, which means that there are theoretical ideas and maybe blueprints for experiments. And then there are some great experiments that really push the boundaries of everything we know about quantum experiments. And they prove that some of the aspects that have been predicted, they exist, and they can be measured. And so that's, I would say, if you want the practical side of it. And we're, I think, probably at a stage where we understand where we want to go, and we understand why it isn't working yet. And those are 2 very good things to have and to build on. We have a concrete problem to address, and we have somewhere to start.
Very good. So I guess applications in cybersecurity, they make sense to use encryption with quantum computers because they are potentially super fast. Is that maybe one answer?
Yeah, so when it comes to encryption, it's not so much about the speed, but it's about the fact that using quantum systems, you can encrypt in different ways. And so there's 2 aspects of it. If you now send an email and you encrypt it because some sensitive information is in that email, then you might, well, there are different schemes to encrypt it, different ways in what your email program in practice does. But there are some of these schemes that are very hard to sort of hack for our classical computers, but actually are quite easy to hack for quantum computers. Again, at least in principle, once we have these working quantum computers. So quantum computers, on the one hand, could break some, not all, of the existing encryption schemes. On the other hand, you could use quantum physics to create a new type of encryption that is believed to be much more secure than some of the encryption we have nowadays. And that would not be because the quantum computers are faster, but because they have these quantum phenomena that you somehow built into the encryption scheme. Yes.
Yeah, very interesting. And I hope this answers the question about the potential applications in information and communication technology, cybersecurity, and so on. And we had one last quick question that was referring to the temperature topic. Eiko, would you also read that out, maybe?
Yes. So what temperature do you run your experiments?
Yes, thank you very much. Let me first, maybe it wasn't clear enough, make that very clear. I'm not doing any experiments. As a student, I tried to do experiments and it failed miserably. So then I said, okay, let me do theory. That's less dangerous. So my colleagues, however, they are doing the experiments, wonderful experiments, great colleagues. And typically those experiments are, well, at the lowest temperatures that you can reasonably get, because the lower the temperature, the better the data. Sometimes you also want to have experiments at higher temperatures, so you want to see how the data evolves as you make the system cooler and cooler. There's also lots of interesting things happening if you change the temperature, but most of the time you aim at going to very low temperatures, because then the data is just not as noisy and nice and clean. Now, the lowest temperatures that you can reach are roughly of the order of minus 270 degrees Celsius. So for people who are familiar with the Kelvin scale, so we talk about a few Kelvin, a few hundred microkelvin. I've seen experiments with a few 10 or so microkelvin, depending also on the system, right? Some systems you can get colder, but that's roughly what people want to do. They use the best fridge they can have.
Thank you very much. That's interesting, and also tying it a little bit to the classical physics, so thermal physics and so on, connecting also to the issue of temperatures. I would really like to recommend again everyone who is interested in the experiments and also in the bigger picture of the research that Tobias is doing and the whole environment to check out the KTQ app and to have a look at the YouTube channel of CTQMat, because there you will find further fantastic material that explains the big research topic that the colleagues there at TU Dresden are doing together. So please visit that. I think we will link that on our event page for everyone to check out later. And we are approaching the end of the discussion time. If there are no further discussions in the Q&A, I think we got all of them. Okay, with the questions from the participants. Then, yeah, thank you, both of you. Thank you, Haruna, and thank you, Tobias, for the great presentations. It was very fascinating, and I think it was very nice to see how the research of both of you kind of complemented each other. And now I would also like to thank all of the participants, and would like to hand over again to my colleague at the DWIH Tokyo, Axel Karpenstein, to wrap up the discussions and close our event today with some remarks on the overall event. So Axel, please, I hand the microphone to you.
Yeah, thank you very much, Myra. As mentioned before, I tremendously enjoyed both presentations today. So thank you very much. We come to the conclusion of our fascinating exchange today, quantum physics and quantum technologies. I'd like to express my thanks once again for everyone's active participation. It's been a privilege to hear from our distinguished speakers and to witness such insightful discussions on the future of quantum technologies and the importance of international collaboration. I represent the Tokyo office of the German Center of Research and Innovation. It's a network of 6 such centers worldwide. We're located here in Tokyo. We have this problem. We have the acronym DWIH. It makes sense in German. It stands for German Center for Research and Innovation. It's hard to remember in English, but I used ChatGPT to come up with a quantum-related way to remember it. And ChatGPT told me a good way would be discrete wave functions and interference in Hilbert space. Frankly, I don't understand it, but it sounded rather funny, and I hope both speakers will find it funny as well. In either case, as DWIH Tokyo, as German Center for Research and Innovation Tokyo, we connect German and Japanese researchers, and we provide a platform where cutting-edge research and innovation can be driven forward, and real-world applications of science. Today's talks, I think, have highlighted the immense potential of quantum technologies. We heard about quantum computers, quantum cryptography, different ways how to utilize quantum science. We heard about the connections or the research on black holes and possible implications from that. So I'd like to thank everybody, and especially our esteemed partners, our colleagues from the German Research Foundation, the DFG, and Hiroshima University for their invaluable collaboration in organizing this event today. My heartfelt thanks also goes out to our 2 speakers, Dr. Katayama and Dr. Meng. Thank you very much for your insightful presentations. I believe quantum technologies, and you will hopefully all agree, holds tremendous promise for the future. And through international collaboration, as we saw today, and dialogue, I think we can perhaps fully realize a lot of its potential in the future. I hope the event has contributed to inspiring new ideas for everyone. And I look forward to continuing our discussion outside today's event in the future. Thank you very much, everybody. Everybody in Germany, have a good day. And in Japan, we are almost approaching the weekend. So everybody, please enjoy the weekend as well. Thank you very much.